Hello and welcome to the instruction on exponents and the review of those principles and rules and how to teach them and how to help students who have struggled with math understand them. So here we have the list of rules of exponents from a book, and when students look at this, this may not mean very much to them. Now you can see it well when you multiply, you add the exponents. When you take a power up to a higher power, you multiply them. Well, that's good, but let's go back and see why this is valuable and how to get the student up to the point where they can understand this. So there are actually certain things. So you write it over here and you say, okay, the rule. What is really the rule? Use numbers that they can actually see. Do something like this: x squared times x to the 7th, and be able to say x to the 9th. Then they will say something like, oh, wait, when you're timesing, you add the exponents? Well, yes, indeed. Well, why is that the case? Go ahead and have them write this down. Well, x squared is x times x, and then x to the 7th is 6, 7 of them. Good. And how many do you have now? Well, you have 9 of them. Yeah, right there, that's it. You have a why that happens. Not just that they have to memorize why that is, but yeah, that's 2 x's, and that's 7 of them. And altogether, you have 9 of them. Throw some examples in there. Go ahead and take something like 2 to the 3rd times 2 to the 4th. Now, when they're doing these examples, go ahead and get their calculator out so they can see how it would work. Based on what we're doing, this should be 2 to the 7th. And there is a concern. Some people will try to write 4 to the 7th because 2 and 2. But notice this is 3 2's and 4 2's. We end up with 7 2's. Go ahead and punch that into a calculator and you get 8 times 16 really gives you 128. And make sure they get these independently. Yeah, that'll help them. And then with all of this background, they can then start to understand what this means over here. That, oh, when you're multiplying things, you add it. So that'll give them a little bit different thing. So let's do it with the same thing here. X squared all to the 7th power. Based on this rule, what does it mean you'll do here? Yeah, you'll multiply. So this is the power rule. Yeah, and this is the multiplication rule. Now multiplication gives you addition. That's important. Power to power gives you not a power, not a 2 to the 7th, but a multiplication. That's important. Give you x to the 14th. Now, why does that happen? Well, yeah, what's x squared? Well, that's xx, but let's write as x squared to the 7th power means you've got 7 of these. Yeah, and based on the first rule, what is that? Oh, yeah, that's x to the 14th power. That's exactly what is going on. Go ahead and punch that in, do some. 2 to the 3rd power and raise it to the 4th power. According to this, it should be 2 to the 12th. Well, is 8 to the 4th power really the same as 2 to the 12th? Punch them in calculators and see if that really works. And yeah, they'll be able to see that it works for numbers, letters, everything, that these are actually bona fide real rules. Okay, what's the next one? Well, x to the 7th over x squared. And will they see that? Yeah, they'll be able to remember this better than all these m's and n's and a's. There are 3 variables in their minds here. And really, it's the operation, not the variable m and n, that you're focusing on, that relationship there. And they'll get subtraction. And why does this happen? Well, yeah, you've got 6, 7 of them on top, and multiplication, division, and you get left with 5 of them. Yeah, try that. 2 to the 7th divided by 2 to the 4th. And they'll be like, oh, 7 divided by 4 is 3, or 2 divided by 2 is 1. And this rule will help them to see, no, those don't change. This is just counting up how many 2's you actually have. Well, try it. 128 divided by 16. Does that really give you 8? Indeed, it does. That will give us a good background for why, when you do x to the negative 3, that equals 1 over x to the 3rd. Well, why is that the case? Well, let's try this one and go backwards. What is x squared over x to the 7th according to the division rule? There's your division rule, and here's your negative exponent rule. What happens there if you have x squared over x to the 7th? Well, that's going to be x to the negative 5. Well, look at the y. xx over, yeah, look at that. Did we get enough of them? 6, 7, yeah. When you cancel those, it leaves a 1 on the top, and you have x to the 5th on the bottom. Yeah, that's exactly right. You can actually show that negative exponents just mean that you're dividing based on this. Make sure they see a few examples of 2 to the negative 3, that it comes out to be 1/8. 3 to the negative 4 actually comes out to be 1 over 81, and stuff like that. So they see that a negative exponent is not a negative number but a fraction. That will be one of the biggest things that they have a struggle with, is that negative exponents they will think mean negative numbers. This is also a great tie into scientific notation. When you take something like 5.2 times 10 to the fifth, you are simply timesing by 10, which moves the decimal, 5 times. 5.2 times 10 to the negative fifth, they've learned, you move it the other way. Well, that only means you're dividing by 10 5 times. Okay, here we have x to the 0 equals 1. And they will struggle with that a lot. Why does that work? Let them see it in their calculator. 7 to the 0, and it'll pop out a 1. And 15 to the 0 equals a 1. 8 to the 0 always equals 1. They'll wonder why. Why is that the case? Well, it comes back to the division rule. If you have x to the fifth over x to the fifth, by the division rule, that is x to the 5 minus 5 is 0. Yeah. Anything divided by itself is 1. And so you might help them to understand when you have a 0 exponent, that means whatever you were multiplying by, you divide it off, which is why it comes to 1. It's also really kind of cool if you get to show them something like this. A 2 to the fourth, 2 to the third, 2 squared, 2 to the first, 2 to the 0, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4. And when you do this, 16, 8, 4, 2, and then you look at what these equal, well, that's 1 over 16. Yeah, it's a reciprocal of that guy. This is 1 over 8. This is 1 over 4. That's 1 over 2. And you'll notice that there's a pattern. Every time you have a smaller power of 2, you divide by 2. Divide by 2, divide by 2. The only number that would work in here is 1. And that becomes a 1/2, and then a 1/4, and then a 1/8, and you keep dividing by 2. Or if you go up, increasing a power of 2, you'll get the same pattern. You'll end up with 2 to the 0 equaling 1. So it works the same if you do it with 3 to the 4, 3 cubed, 3 squared, 3 to the first, 3 to the 0. This will always be 1 for every single x. And it's pretty cool to watch that. And the last one, they usually have no problem with anything to the first power, is that. But that's what this table should look like to give students a clear picture of whether this helps them to see what's working, or whether this gives them a better understanding, or whether they like the book. It might be all better, but most struggling students see 3 variables over here that are kind of randomly put together and not understanding exactly why that takes place. Excellent. With these newfound rules of exponents, there is some psychological noise that will enter. For example, if we have something like 3x squared and we times it by 5x to the 7th, yeah, that's going to be 15x to the 9th. And they're like, yeah, we can do it, we can add those, and everything's good. They will try to do something weird when you have 3x squared plus 5x to the 7th. Yeah, that thing doesn't add together. We've got to go back and remember that when you are adding, you can only add like things, ever. So these things don't add. This is BZ cubed right there. Thanks for playing. You can't add those things together. But they'll be like, well, wait, why can we multiply them? Yeah, multiplication never ever assumed that you had like things. And that's important because we now have rules for how to multiply those things. That's really good because you'll have something like this, 3x squared plus 5x squared. And they'll be like, oh yeah, I know how to do that. That's 8x to the 4th. And they'll try adding the exponents. Not true. Adding like things that we did way, way back in arithmetic keeps up the same thing. This is now 8x squared. So you may have to go back to 3 apples and 5 apples. Whereas this up here would be like 3 sheep and 5 penguins. Another confusion is you might have something like 3x to the 4th, y to the 5th, all squared. And they'll, oh yes, I remember how to do this. 3 to the 2nd power is 9. Now that's not multiplication, it's 3 to the 2nd power. Now x to the 4th to the 2nd power is x to the 8th. And they'll be like, wait, why did you multiply that but not the 2 times the 3? The shortcut for power to a power is multiplication. So, and that's y to the 10th. And they'll feel really good about that. And then you'll give them a question like this, and they will try to do that. Just so you know, jumping that 2 in here to give you 9x to the 8th plus y to the 10th. Oh, this is so bad. This is called the freshman's dream. That's actually the name for it. That the younger students wish that would happen when it were so easy, but it turns out that that plus sign right here just ruined your entire life. That's right. Multiplication with polynomials means you have to distribute. So this is 3x to the 4th plus y to the 5th in parentheses times 3x to the 4th plus y to the 5th. And what that plus sign means is you must distribute. When you do polynomials, you have to distribute like that. That's where you get 9x to the 8th plus, 3x to the 4th, y to the 5th, 3x to the 4th, y to the 5th, and plus y to the 10th. Good. Ooh, now we can combine like terms right in there, and we get 9x to the 8th plus 6x to the 4th, y to the 5th, plus y to the 10th. Oh, very good, very good. Yeah, multiplication, you don't have to have like things at all, but with a plus sign, you better do that. Now, you should note that if I have something like 2x plus 5, and I multiply that by, let's go ahead and do a long one here, 3x squared plus 4x minus 7, and we multiply that through. Yeah, this is multiplication of polynomials. It's just the distributive property over and over. We get 6x cubed plus 8x squared minus 14x. These colors may help you in illustrating how to multiply polynomials correctly to students. Notice how the orange guy went through and gave us the orange ones. Then when the green guy goes through, you have plus 15x squared plus 20x. And when you line them up in the right order, yeah, it's nice. That may give them some order and structure to multiplying their polynomials. Now, notice we didn't do it on this one, and it can go straight out. You just collect like terms, and you're ending up with 6x cubed plus 23x squared minus 6x minus 35. All right, now we multiplied, notice here we multiplied a binomial by a trinomial. What's 2 times 3? Yeah, we got 6 full terms down here. When you have a binomial times a binomial, how many terms do you have down here? 4. So some of you may be familiar with that acronym FOIL. Yeah, FOIL right there. What is FOIL? Well, it means it's a reminder for students to remember not to do this freshman's dream thing, actually. It's a reminder that they are supposed to, when they multiply these out, take the front 2 times them together, the outside 2 times them together, the inside 2 times them together, the last 2 times together. And it spells FOIL because you get 1, 2, 3, 4. It indeed is a 4-letter word, and it's meant to remind you that a binomial times a binomial, or a binomial squared, will always have 4 terms when it comes out, and then you'll combine like terms down here. So if you just did the 2 terms, you have forgotten to FOIL. Notice FOIL does not work on anything that is not a binomial times a binomial. Here we had the binomial times the trinomial, and we had, front 2 times together, and then the last 2 times together. But notice this doesn't really help us with OI or whatever. So this acronym is only helpful for a binomial times a binomial, and some students choose to use it and use it as a replacement for distribution or multiplication of polynomials, which isn't technically appropriate. But if they're used to that wording, go ahead and let them keep using it, but help them understand it's really a super distributive property that's going on. Of course, if you had something like this, 3x plus 8 to the 3rd power, there isn't a nice way to do this. You actually have to take 3x plus 8 times 3x plus 8 and multiply those out using FOIL if you like, but super distributing, and then take that and do 3x plus 8. And that should help you finish up with exponents. Good.